Hello everyone. So this is the first tutorial of the course Drone Systems and Control, where we will have a recap on vectors and coordinates. These are the concepts which will be required in the later lectures of the particular course. So for that we are having a refresher kind of tutorial in this particular talk. So this tutorial gives a recap on the concept of vectors and difference from scalars, representation of vectors graphically and algebraically, vector operations such as addition, subtraction and scalar multiplication, and dot and cross products of the vectors. For many students, this particular tutorial may be the topics covered in the tutorial may be very familiar, so they can listen to this tutorial as a refresher material. Those who are not familiar to these materials, we will suggest them to go to the go through the reading materials so that they can understand all these concepts and then make use of those concepts in the later lectures. Okay. So first comes the introduction to vectors and coordinates. In mathematics and physics, vectors and coordinates are kind of foundational concepts. Vectors represent quantities with both magnitude and direction. The coordinates help us locating vectors in space as points, and this tutorial explores the basics and applications of vectors and coordinates. So what is a vector? A vector is a quantity that has both magnitude and direction. The examples are like velocity, force, displacement and so on. Generally it is represented by arrows in diagrams, as you can see here. This is a vector v1, this is another vector v2. The notations are given as these particular things like bold v or v, an arrow on the top to just represent that this is a directional thing and it has a proper direction. Scalar, only magnitude will be there like temperature, mass, speed, etc. But in case of vector, both magnitude and direction are important. The first thing is velocity, and the second thing it is, you can think of any other vectors like force. So it is important to distinguish between these two, like scalar and vector, properly so that you can do analysis in physics and engineering. So two vectors you can see here, one is vector v1, another is vector v2. These two vectors are not equal if either their magnitude or their directions or both are different. If they are same, like two vectors, vector v1 and vector v2 are of same magnitude, that means the length of the vectors, and in the same direction, that means they will be collinear like this, then and only then we can say that the two vectors are equal. So vector representation in coordinate frames are something like this. The vectors are represented as directed line segments. So the vector will have one origin which comes here, and this is the arrow which represents the magnitude and direction of the vector. Now when it comes to the coordinate frame, then the vector is represented as a point P. This is the point P. In two-dimensional scenarios, this particular vector V is represented as an array where the first element is the x coordinate in the coordinate frame and second one is the y coordinate. So in 3D, this vector V becomes x, y and z. So the components are the projections on the coordinate axis. What does that mean? So in this particular thing, you can see if the vector is projected on the x axis, then we get the x coordinate of the point P. If we project on the y axis, then we get the y coordinate of the point P. Okay. So in coordinates, vectors are represented as arrows, as we have seen in the last slide also. This coordinate system is used to define vector components. When it is a Cartesian coordinate system, then we have three axes x, y and z for 3D. If it is a 2D, then it will have only two axes x and y. If it is 3D, then it will have three axes x, y and z. Okay, so when it is a two-dimensional system like this, then the Cartesian coordinate system is given as x and y axis, and this is the vector. This vector has a tip here which is represented as a point P, which has a coordinate of x and y. So this point P can be represented as Pxy with its coordinates, whereas the vector r can be represented as a vector xy, which is an array. When we represent it like this, then it is a Cartesian coordinate system which can be represented as this x and y axis. But when it comes to polar coordinate system, which is very important in drone applications also, in polar coordinates the vector is represented with one parameter r and another parameter theta, where r represents the vectors with its length and theta represents the angle which it makes with the positive x axis. Now if you see here, this r, this y coordinate of the point P can be represented as r sin theta and x coordinate can be represented as r cos theta. So in the same figure we are showing both the Cartesian coordinate system and the polar coordinate system. Okay, the choice of the system depends on the problem. Now when it comes to 3D, if we draw a vector here, say similarly a point P, so this particular point will have a coordinate x, y and z. Now when we make a projection on the xz plane, then this looks like this. This particular angle is called azimuthal angle, and this particular angle where it captures the elevation of the vector from xz plane or horizontal plane is called elevation. The elevation can be represented by theta, azimuthal angle can be represented as phi, and the vector is r. So in three-dimensional polar coordinate system, the vector can be represented as r, theta, phi. Next comes vector magnitude. What is the magnitude of the vector? The directionality is shown by the arrow. What is the magnitude? The magnitude is the length of the vector. It represents how long the vector is. So if we see in this particular figure, you see that this is the origin of x and y axis and the coordinate system. We are showing it in Cartesian coordinate. So this particular vector r, what is its length? Its length is from this point to this point. The total length is the length of the vector. It is a scalar quantity. And what is how is it calculated? It is calculated by Pythagoras theorem. Since this particular length is x and this particular length is y, then the length of the vector is square root of x square plus y square. One example, if the vector is represented as 4 minus 3, if we draw it, it should be something like this. This is x axis, this is y axis. So the vector 4, 3 will be somewhere here. This point where this is minus 3, this is 4, 0. Now if we want to see what is the length, then this length will be given as this particular length 4 and this particular length 3, 4 square plus 3 square, which is equal to 5 square. Then this the length of or magnitude of the vector is square root of this, that means square root of 5 square equal to 5. So in this particular scenario, we can write that the vector v has a length or magnitude of 5. Now comes another concept which is very important in vector algebra and coordinate systems, that is called unit vectors. Vectors with magnitude equal to 1 are called unit vectors. So the unit vectors indicate only the directions and not magnitude, because the magnitude itself is 1. There are common unit vectors like I, j and k cap, which are which shows the directionality in x, y and j axis. So to get a unit vector from any vector v, what we need is that we have to divide the vector by its own magnitude. Fine. So the unit vector of any vector v is represented as v cap, which is equal to the vector itself by its magnitude. That means all the components of the vectors v1 to vn in n-dimensional plane all divided by the magnitude of the vector. Okay, so we can see one example here where the vector is 2, -3 and 6. That means it is in 3-dimensional plane. X coordinate is 2, y coordinate is 3 and z -3 and z coordinate is 6. So when we try to find the length of this particular vector, it comes as 2 square plus -3 square plus 6 square equal to 4 plus 9 plus 36 equal to 49 equal to 7. So we can tell that the length of this vector v from this particular representation is 7. Now if this particular vector 2 -3 6 is divided by 7, that means all the components are divided by 7, then it looks like this, and this forms the unit vector v hat. Okay. Now comes position vectors. A position vector denotes the position of a point relative to the origin. We can see it from here. So in the Cartesian coordinate system, if this is the origin, this is the vector with point P tip with coordinate x and y, then as an example we can show that a point 4, 3 has a position vector r equal to 4i plus 3j. How is it coming? See, this particular point where we are getting the projection on the x axis is represented as 4, 0 and the y axis projection is represented as 0, 3. The unit vector towards x axis is I, the unit vector towards y axis is j. So this particular vector, when we show as a position vector, it is represented as r equal to 4 times I plus 3 times j. So this particular idea of position vector can be used to calculate distances and displacements. Now comes some important concepts on vector addition, subtraction and scalar multiplication. So when we talk about vector addition or subtraction, it is a kind of component wise addition and subtraction. So it combines two vectors. When it about addition, it combines two vectors to produce a third vector. How is it? See, the algebraic rule is something like this. There is one vector a hat, vector a arrow and another b. When we represent it in coordinate frame, it should be something like this. The first vector a will be a1 and a2, those are the x and y coordinates. The second vector b will be b1 and b2. So when it's a vector addition, it will be a component wise addition. That's why a plus b becomes a1 plus b1 and the another one becomes a2 plus b2. So a plus b looks like A1 plus B1 and A2 plus B2. It can be represented like that also. Now, what will be the addition of two vectors can also be found from triangle or parallelogram rule. We'll request the students to go through these concepts from any textbook. Okay, when it comes to vector subtraction, it is something like this: A minus B is equal to A1 minus B1 comma A2 minus B2. That means what we are doing here is that A minus B equal to A plus minus of B. That means the reverse direction of B is added with A to get the subtracted values. Okay. Now comes multiplying a vector by a scalar. So when we go for scalar multiplication, we can see that when one particular vector is multiplied by a scalar, it changes the magnitude. It can stretch the original vector, shrink it, or reverse its direction. So when we show it mathematically, a vector V multiplied by a scalar k becomes kV1 and kV2. So kV says kV1 and kV2. Now when this particular vector, the scalar k, this k is greater than 1, then the vector is stretched. If it is, the k is between 0 and 1, then the vector shrinks, and if k is negative, then there is a change in the direction. It reverses the direction. So we can come here to see some examples when there are two vectors A and B like this, then A plus B are like 2 plus 1, 2 plus minus 1, which is 1, 3 plus 5, which is 8. So A plus B becomes 1, 8, which can be represented as this also. Two other set of vectors A 4 comma 1 and B 2 comma 5, we can see that A minus B becomes 4 minus 2, that is 2, 1 minus 5, that is minus 4. So A minus B becomes 2 minus 4. Now another vector V, which is 3 minus 2, and K, the scalar through which the V will be multiplied, is minus 2, then KV becomes minus 6, 4. So these are the examples of addition, subtraction and scalar multiplication. Next comes another very important concept called dot product. The definition of dot product is that it is a scalar term coming out of two vectors. It measures the projection of one vector onto another. So if you come here and see this particular image, so this image has two vectors A and B. Okay, so when we talk about dot product, we represent it like this: A dot B is the dot product of the vectors A and B. What is happening here in A dot B, where A is the terms A1, A2 and A3, and B is another vector which has terms B1, B2 and B3, then the dot products are like kind of component wise multiplications: A1 into B1, A2 into B2 and A3 into B3. So the dot product of A and B becomes A1 B1 plus A2 B2 plus A3 B3. When we see it from a geometric perspective, then A dot B is equal to the length or magnitude of A multiplied by the length or magnitude of B multiplied by the angle, cosine of the angle between these two vectors, that is theta. So geometrically A dot B can be represented as this particular term, magnitude of A into magnitude of B into cosine of the angle between the two vectors. Okay, so this particular idea of dot product measures how much two vectors align. How? We'll show it with an example. This particular idea is used to calculate the angle between two vectors. So if we know that what are the dot products between two vectors, and if we know their magnitudes, then the cosine of the angles can be found with this particular formula, where cosine of theta becomes AB dot product by magnitude of A into magnitude of B. So through that we can get the angle theta. That's how it helps to calculate the angle between two vectors. Okay, this particular dot product is positive when the vectors point in a similar directions and negative when it is opposite. Okay, let's come to one example where the vector is 2, 3. The first vector A and the second one is 1, 4. When it comes to finding the dot product, it becomes 2 multiplied by minus 1 and 3 multiplied by 4. So totally it becomes 10. Okay, now we can check what is theta from here. So A, the magnitude of A is something which can be found from here, this particular vector. Magnitude of B also we can find from here, and then if this particular term 10 is divided by magnitude of A and magnitude of B, then we get the cos theta, cosine of theta. From this theta we can from this value of cos theta we can get the angle between theta. Now we are telling that the two vectors, how much they are aligned is measured by dot product. So let's take two vectors which are similar, 2, 3, and another vector is also 2, 3. What will be the dot product? The dot product will be 4 plus 9, right? What is the magnitude of A? The magnitude of A is square root of 13, magnitude of B is square root of 13. That means what is the cos theta? The cos theta is 9 plus 4 equal to 13 by square root of 13 into square root of 13 equal to 1, which means that the angle between this is 0 degree. That means they are aligned. So that proves that when the vectors are completely aligned and they are having same magnitude, same direction, everything, then the angle is coming as 0 degree, and accordingly we can conclude other things from the concept of dot product. Okay. The second, in this way, the second important concept of product is cross product, where two vectors, when they we get the cross product of two vectors, it results into another new vector called the cross product vector. So it is something like this: a vector A and another vector B. If we take the cross product, then it is computed in terms of determinants where I, J and K are unit vectors along x, y and z directions. Now the vector A is A1, A2, A3, the another vector B is B1, B2, B3, and accordingly we get what should be the cross product. Also geometrically we can say that the cross product, magnitude of the cross product, A cross B is the cross product, magnitude of that is the product of magnitude of A, magnitude of B and sine of the angle theta, where theta is the angle between these two vectors A and B. Okay. Now one important concept which we should notice here is that a cross product is a vector. It comes as a vector where the first component towards the x axis is this multiplied by the respective unit vector, the second component is this with the unit vector, and the third component is this with the unit vector. So it comes as a vector, right? However, when we are talking about dot product, it was a scalar. So this is a distinction which we should very carefully check and we should not forget. Okay, so cross product produces a vector orthogonal to the plane to the two vectors. So when we talk about a vector A and another vector V and we take a cross product, then the cross product comes like this. This is the cross product which is orthogonal to the plane of two vectors. So if we find the plane of two vectors A and B, then cross product vector is orthogonal to that plane. The magnitude of the cross product, that means this particular term, is equal to the area of the parallelogram formed. So from the parallelogram rule we can check that this particular parallelogram where one side is formed by the vector A and another is formed by vector B, the area is equal to magnitude of A, magnitude of B and sine of the angle theta. So we can conclude that the magnitude of cross product represents the area of the parallelogram formed. There is one example which you can just carry out. There is one vector A, another vector B with this coordinates. What is the cross product? Okay, so in this tutorial the focus is on recap of vectors and their operations. The recap of coordinate frames are also carried out here. For further reading, we propose this book called Vector Analysis by Murray and Murray R. Spiegel, where you will get more advanced concepts on vectors and coordinates, and whatever we have gone through this tutorial you can brush up from this material. Thank you.